Welcome friends, welcome to JCE Connect. This is part 2 of tachometric surveying, where we are going to derive the few of the equations of principle of stadia tachometry. We are going to derive an equation for the stadia tachometry. Then we are going to derive the distance formula by using the tachometry, and then afterwards we are going to derive few of the equations related to the fixed hair method. So there we are going to have line of sight in horizontal and line of sight inclined. So we'll see one by one how it will be there. So first we are going to see the principle of stadia tachometry. Now here if you see this stadia tachometry here, as I said that there are two things that what you have to keep in mind when we are going to call an instrument as a tachometer. Basically you are going to use a theodolite only, but if that theodolite is having the diaphragm, then we are going to call it as what? Tachometer. And with that, if it is having the analytic lens, then we are going to call it as what? It as tachometer. Now the important of that analytic lens is, when you will be having the analytic lens, then K is becomes what? K will become 100 and C will become 0. Now what are those K and C? K and C are the what? K is the multiplying constant, where C is the additive constant, constants of tachometry. Now we are going to derive that constant, how those constants will be there, that we are going to see here. So thorough the identification of K and C is principle of stadia tachometry. Now if you see here, the stadia method is based when the principle that the ratio of perpendicular to the base is constant, right? The stadia method is based upon the principle that the ratio of perpendicular to the base is constant. Now if you take a similar isosceles triangles, now if you can see that we are having here, now if you take this OCA, also you can take OCB2. Now you can compare this larger triangle with remaining smaller columns. You can compare OCA with OC2A2 with OC1A1 with this also, right? So that is the thing that what we are going to take here. Now from the figure, where you will be having OA and OB, right? If you take this here, if you take this OA and OB, here you will be having OA and here you will be having OB, be equally inclined to the center ray OC. This is the central ray OC. Now here you can take, say, how to carry this experiment. Set a instrument at station here and keep the staff at equal distances, right? So that you can have the similar isosceles triangles will be there. Then you will be having the readings like this, 3 crosshair readings. You getting this? So here OA and OB equally inclined to the center ray OC. Now with this, now here what you can do is that let A2 B2 and A1 B1 be the staff intervals. Now here if you take 3 staff, A2 B2 and A1 B1, similarly A and B are the staff intercept, evidently. And if you take the triangle, what is going to happen here? Here you can have the, as I said that similar triangles are there, then what you can have is that OC2, if you take this OC2 divided by A2 B2, that equals to OC1 divided by A1 B1, that equals to OC divided by AB, right? You can easily compare this thing. Now if you see this figure, what I given here, this is at full angle, this is beta, the full angle is beta here, right? You can see this is beta, and the half of that is beta by 2. Okay, so now if you take, see what is this right? What is this OC1 divided by A1 B1? What is this OC2 divided by A2 B2? Now these, right, if you take these, now see here, if you take this, if we will take one term here, right, if you take this OC2 divided by A2 B2, A2 B2, now what is going to be this? Now first you are supposed to find out the, what you can do is that you can find out the trigonometrical function from that, right? OC2 divided by, see what you can get a trigonometrical function here for this theta by 2 or beta by 2. If you take beta by 2, what is going to be there? Now here I have shown that here, if you take a beta by 2, now beta by 2, it is going to be, now if you see this beta by 2, what is this beta by 2? Beta by 2 is OC2 divided by A2C2, right? If you check out that, if you check out that figure here, right? See this beta by 2 is, what is this? This is going to be OC2 divided by this A2C2, this side, right? This is going to be beta by 2. Now what is going to be total beta by 2? It is going to be 2 times of, you can write like this also, 2 times of 2OC2 divided by A2 B2. Now here I have shown that, right? You can easily see that thing here. I'll be showing. If you take this, now here it is going to cot beta by 2 is equal to 2 times of OC2 divided by A2 B2, right? Then half of cot beta is equal to, what is going to be? That is going to be K, and this is according to the figure. Half of cot beta is equal to K. Now that you have to understand, or you have to remember that thing. Now how we are going to take this K, constant K, right? That constant K is, now if you take this, that constant K, see here I have shown, constant K is half of cot beta by 2. Now this whole thing, as I said, that if you are using the analytical lens, this whole thing is going to be 100. How that K is going to be 100? Now this constant K is entirely depend on the magnitude of angle beta, right? Magnitude of angle beta. And if beta is made equal to the 34.22 seconds 0.64, then K becomes 100, right? Now if you take this, see here, beta by 2, this is 34 degree 22 seconds 0.64 divided by 2, it is going to be, here it is 17 degree 11 seconds 0.32. If you put this much here, then it is going to be 100, then K is going to be 100. That you have to understand, means whatever thing you are going to take, the angle between the intercept is going to be what? 34 degree, it is here, so you can see this. Now it is going to be 34 degree 22 seconds 0.64. And in fixed hair method or steady system, the central hair are fixed at the distance such that the line of sight through these hairs make an beta by 2. Means if you take this, right, these will be fixed one, and whatever angle it is going to form here, that is going to be, see, 17 degree 11 seconds 0.32, right? So that the multiplying constant K should become 100. That we have to keep in mind. That is a very important thing that I describe here. That is, that we called as what? This, in this case, the distance between the staff and point O will be 100 times the staff intercept. Now that is what you have to keep in mind. Now what is that, what you are going to consider, what you are going to conclude from this derivation? That what we are going to conclude is that, now if you are having a beta, or the angle between the hairs, that equals to 17 degree 11 seconds 32 seconds. Now if you are having a whole angle as 34, sorry, it's not degree, it's minutes, right? 34 minutes 22 second point 34. If you are having this, then only it is possible to get K as 100 and C as 0, right? That is an important conclusion what we can make here. K is equal to 100 and C is equal to 0. This is going to happen only if you are having the angle of 34 minutes 22 seconds point 64, and that is going to be there just because of analytical lens. If you don't have that analytic lens there, that angle is not going to be 34 minutes 22 seconds. Because of the analytic lens, this angle is going to be 34 minutes and 22 seconds 0.64. That's what we have to understand. Now we're going for the next derivation. Next derivation is, now the next derivation is about the principle of stadia. We have seen this principle of stadia here, right? Now this next derivation is about the theory of stadia tacheometry. Means here we are going to determine the d, that is the distance between the instrument station and the object, and that we are going to determine based on the focal length, based on the that is interval between the two stadia hairs, based on the staff intercept, based on the distance of vertical axis. Now by using all these things, we are going to determine the distance between the instrument and that object. Now if you zoom, now if you get zoom this figure, you can see that what things we are going to see here. I'll try to show you here. We are having an instrument here. This is the instrument station center right? And from here, this is the telescope, this is the optical center O, and then from here we are sighting an object. This is our object, right? This is our object. Now see here, slider is there, so I'll try to hold this, and this is here, this is our object, right? This is the object, that is AB is the object here. So that we are going to sight here, and that sighting will be like this, and the whatever the distance between upper stadia and lower stadia is there, that we are going to call it as one staff intercept, that we are representing it as S. And then few more things that you have to understand based on this figure. See, as I said that this is the optical center here, this is O is the optical center, right? M is the instrument center, F is the focal point here. Then you will be having a reverse image here, that is B is going to upside and C is going to be this A is going to be downside, and this here we called as this distance between the reverse image, that is B and A, is going to be I, that we called as what I it is an interval between the two stadia here, whereas S is the staff intercept, right? That is distance between upper stadia and lower stadia, that is staff intercept. You getting this? Then we are having a D. D is the distance, a small distance between the vertical axis. Here you will be having a vertical axis. You can see that you will be having a vertical axis, distance between the vertical axis and the instrument that is of the optical center O, right? Then remaining, what else is remains? F is the focal length. Here you can see this F is focal length, right? I'll show you here. Here this is the F is the focal length. This distance from the optical center here, it is going to be a focal length. Then F1 and F2. F1 and F2. F1 is the horizontal distance of staff from the optical center to the object. Horizontal distance of staff from the optical center to the object. This is going to be F1, and F2 is, see, from the F2 is the distance from horizontal distance from crosshair from the object, right? Crosshairs to the optical center, right? Crosshairs to the optical center. See, this is F2 is the crosshairs to the optical center. This is going to be F2, and D is the, as I said, that it is the distance from the instrument station and the object, right? So this is going to be your D, right? Now how to get this D? See, it is very easy. This D is equal to, see this, what is this? D is equal to, this D is equal to, this is F plus this is D, right? F1 plus D, right? Small d, F1 plus small d. Now from this figure, what we are going to have? We are going to have D, capital D is equal to F1 plus small d, right? So from here to here it is, right? So this plus this is going to be your capital D. Now that D represents the distance, right? So F1 plus D, this we have to keep in mind. What is D? D is equal to F1 plus D, and I elaborated all the see here, I elaborated all the points there, whereas O is the optical center, A, B, C are the three lines of sight corresponding to the three wires, right? Three threads. Then small a, b, c are the top, axial and bottom hairs of a diaphragm. AB, small ab is the eye, that is the interval between the uh, two stadia hairs. S is the staff intercept. Then F is the focal length of objective. F1 is the horizontal distance between the staff and optical center. F2 is the distance between the that crosshair where you will be having small ABC and the optical center. D is the distance between the instrument station M and optical center O, whereas capital D is the distance between the staff from the vertical axis of instrument, right? Means from the staff to instrument station M, whereas M is the center of instrument. So by using all these things, we have got this formula. It is very important one. D is equal to F1 plus D. Now what we can do with this F1 plus D, I'll show you here. Now if you check that formula, D is equal to F1 plus D. So here F1 is unknown, D is also unknown. So it is very difficult to work it out on that where the two things are unknown. But it will be very easy if we convert this thing in the form of S and I, because S is also known and I is also known, that you can easily find out the distance D. But you have to convert all these things in the form of S and you can call it as yes and I. In the form of that, you have to use yes, you have to use I, because both the values are known, right? If you perform it on the site, you can get the yes and I value. As I have written here, that since the rays BOB and AOB, right, passes through the optical center, they are straight to that. So you will be having a triangle AOB and triangle small AOB. I'll show those triangles here. Now here you can see that what we are going to have. We are going to have two triangles, small AOB triangle, and we are going to have a capital AOB triangle. Now by using these two triangles, we can have a equation. What we can have a equation? See, if you check this, we are having F1 here and we are having F2 here. So F1 divided by F2 you can do. F1 divided by F2 you can do based on these two similar triangles. Similarly, you can do S divided by I. So you can have a relation between all the sides. So you can have F1 divided by F2, that equals to S divided by I. Now if you come here, you can see that here, right, we are having see what things we are going to have here. Here we are going to have this F1 divided by F2, that equals to S divided by I, that we are going to consider it as equation 2, whereas that D is equal to F plus D, that we are going to consider as equation 1. Now based on the conjugate focal length formula, all of you know that what is the conjugate focal length formula. That formula I have written here, that is 1 by F 1 by F equals to F1 1 by F1 plus 1 by F2. This we are going to call it as what? Conjugate focal length formula. This is the formula number 3. Now if you multiply this whole formula, formula number 3, right, if you multiply this whole formula number 3 by F1, then what you are going to get? Now see what we are going to get. If you multiply F1, we are going to get, see here, F1, this F get cancelled, so F1 will remain here. 1 by F1, F1 get cancelled, so F remains here. F1 divided by F2 is going to be there. So I can write this here, F1 remained, I have written here. Then here F is going to remain, plus I can write this F1 by F2. See here, this is F1 and this is F2. F1 by F2 into F, that what I can write here, into remain this F, I can write it here. So this I called as equation 4. Now if you compare equation 2 and 4, or you can substitute equation 2 in equation 4. Now what that equation 2 is there, that is here, right, that is F 1 by F2 divided, that equals to F1 by F2 equals to S by I. Now if you take that, now what you can write here, you can substitute that S by I. So that is F1 is equal to F plus S by I into F. Now the horizontal distance between the axis, that we know that is what is that, d is equal to f1 plus d. So you can easily write that f1 value whatever it is there in this equation, in the equation 1 you can call it as, here this is f1 value you can put here in this equation, right? So that is going to be, see, d is equal to s by I into f plus d. This I can take separately, so I can write it as f plus d. So it is going to be, see what it is going to be, d is equal to f by I into s plus f plus d. So here in terms of, see this f by I can take a value or I can take a constant k, and this in terms of f plus d I can take a constant c. So what I'm going to call it as, I'm going to call it as k f by I as a multiplying constant and c f plus d as a additive constant. So we are going to have a formula, d is equal to ks plus c. Now this is the important, very important formula that what you are going to have. The same thing I have shown here, that is, see, the above equation is known as the distance equation, where k is f by I called multiplying constant and c is equal to f plus d called additive constant. Now this is what for the distance from the tachyometer. Now this is the general equation, but if you take the cases, as I said that we are going to discuss only the stadiometer, in that also we are going to discuss only the fixed hair method and movable hair method. My concentration will be there on the fixed hair method because here we are going to have two cases. So we'll see those two cases now. So my friends, we are going to see the first case in the fixed hair method, that is case 1, when the line of sight is horizontal and staff is vertical. Here you can see this line of sight is horizontal and staff held is vertical, right? So this is the case 1 in fixed hair method. Now if you see this, the tachyometer is set up at A. So here I am going to set the tachyometer and I am going to keep my staff here at B, right? So first step what I'm going to do is that tachyometer I'm going to set at A, and then I'll be making sure that no, the vertical circle should read 0 0. When the vertical circle should read 0 0, you will be having the what no, a truly horizontal line of sight you will be going to get. Because see, if you know the theodolite as you are using as a tachyometer, if you do the vertical circles to read 0 0, your telescope will be truly horizontal, means your line of sight will be perfectly horizontal. So that first thing you have to do. The second thing what you have to do is that you have to keep a staff at B. The 3 hair readings are taken on the staff B, right? That is the second step. Third, what it says, the staff reading on benchmark is also known. So you should know the staff reading on benchmark. Here what we are going to have here, the staff reading on benchmark is your H1. Then you will be having, see this condition here, the no, as I said that the difference between the upper and bottom staff reading, crosshairs, those we called as what, staff intercept. Yes, and from the center crosshair reading to the ground, that we are going to call it as what, H, right? Small h here. Then from this figure, if you see this figure, you will be having H1 here, that is the staff intercept at staff reading taken at benchmark. You will be having small h, that is the central right hair reading from the ground, and then you will be having the S, that is the staff intercept. Now here the D is the distance between A and B. Now you can see, let D is equal to horizontal distance between A and B, S is the stadia intercept, and H is the staff reading taken on benchmark. Now we are going to have the formula D is equal to Ks plus C. This is the formula you can use, as K is also known, S is also known, C is also known. So once if you get the S value, once if you get the distance D, right, so you can easily determine the what this distance H is also known, and where you are going to get small h1 is also known. So here you can use this formula D is equal to Ks plus. See, this is the formula to get the distance, and to get the RL, see how it is very simple here to get the RL. Now if you project this, if you know, now if you project this, I'll show you. Now if you see this, RL of benchmark is known, RL of benchmark plus S1, you are going to come at the line of sight here, minus H, if you do this, you are going to come here, is it, at the benchmark, means at the ground point, right? So this what you have to keep in mind here. As I said that elevation of RLB is equal to RL of line of sight minus that central crosshair reading small h, right, that here, right? So it is RL of RL of, see this, RL of this is important, RL of that line of sight, this we call as what, line of sight. RL of line of sight is important, minus H if you do, you are going to get this. Now how to get the RL of line of sight? RL of line of sight is benchmark, RL of benchmark plus H1, you are going to come here, that I have shown here. This is the formula for line of sight horizontal and staff held vertical. Now this is the case 1. Now what if the staff held is vertical but the line of sight is inclined? That is case 2. We are going to see that how to get that. Yes my friends, this is case 2, distance and the elevation formula, where the line of sight is inclined and the staff held is vertical. Now here you can see this line of sight is inclined, right? See, you can see that dotted line of sight is inclined and staff held is vertical. In this condition, how to get the now distance and elevation formula? Now if you see that you have to set instrument at A, D is the distance between A and B, that is the instrument and the staff, where H is the, see again, H is the central hair reading to the ground and V is the central hair reading to the, if you know, get the line of sight truly horizontal, that is we call it as a line of collimation. The distance from the line of sight and line of collimation is V, and staff reading is the upper reading and lower reading, that distance we call it as what, staff intercept, yes. Then here you will be having H1, the benchmark reading what you have taken on the benchmark, that is H1, and then you will be having angles here, right? If you see this, what else you will be having? See, you will be having angles. This is theta 1 is the angle between these two lines and beta is the angle between the intercept, staff reading, staff hairs, right? That is beta, and this distance is L, whereas this distance is D, right? So we are going to see how to get this V, H, right, and D. Okay, so the things what will be there, that I am going to read. The tacheometer is set at A and the staff held at station B. The vertical circles to set 0 0 and the staff reading taken on the benchmark. First you have to take the benchmark reading. Yeah, you have to make a 0 0 reading. Your telescope will be this. Then take a benchmark reading. You are going to get H1. Then next what you have to do is that then telescope is raised till 3 crosshairs cut at the portion of a staff and telescope is clamped. Then the vertical angle theta will be measured. Vertical angle theta is going to be measured, right? And 3 crosshair readings you have to note down. The upper, center and lower crosshair readings you have to note down. Now after doing that, see, theta is going to be angle of inclination, that is line of sight, from the horizontal, the angle of line of sight from the horizontal, and D is the horizontal distance between the instrument and the staff, where V is the vertical distance from the instrument axis to the central crosshairs, and H1 is the staff reading on benchmark, H is the central reading on the staff at B. Now with these details what you have to do is that if you take, now you are going to determine D as well as you are going to determine V here. The two very important things are there. Now if you take the triangle from the figure, now what you are going to do is that, now if you check this figure here, right, what you are going to have from this figure, you are going to have from this figure cos theta. Cos theta is equal to adjacent by hypotenuse. Now if you see this adjacent by hypotenuse, this is the adjacent side, this is the hypotenuse side. So D by L I can keep there. So D by L is the is the cos theta. Now D is equal to, because we want D, so we are going to get that D. D is equal to L cos theta. This we can keep it as equation 1. But this L is going to be K dot S dash C. Now you know that the distance, right? The distance between the central and the staff, it is going to be K into S dash plus C, that is going to KS plus C, right? So S dash I have taken because we are not going to take S, but we are going to take this S dash, right? We are going to take this S dash, right? Now if you see here, S dash is going to be like this, but S is going to be like this. Here also in this figure you can see that S dash and S, here I have shown S dash and S. So right, so here that we are going to use here, right? What we are going to use? We are going to use L is equal to K into S dash plus C. So cos theta is going to be, see, cos theta is going to be S dash by 2 divided by S by 2. Now that if you take this, cos theta is equal to S dash by 2 divided by S by 2. Now that is going to be S dash by S. So S dash is S cos theta, S dash is S cos theta. Right, here I have shown S dash is S cos theta. Now from equation 1, see D is equal to L cos theta. If you put that L value here, it is going to be K S dash plus C cos theta. Now you can write that S dash value is this, right? So that S dash value you can write, that is K S cos theta plus C into cos theta. So we can multiply that here, K S cos square theta plus C cos theta. Now this is going to be your formula for horizontal distance. This you have to keep in mind, that distance formula is going to change when the line of sight is horizontal, and distance formula is going to change when the line of sight is inclined. Now here this is the line of sight inclined, you will be having the distance D is equal to ks into cos square theta plus C cos theta. Now what about the vertical reading V? What about the V is the, right, very important reading, that is the no that is the central reading, central crosshair to the no that inclined crosshair to the line of collimation. That distance we called as what? V. So we have to determine that V. Now if you see the figure, from the figure what we can get is that V is equal, sin theta is equal to V by L. Now if you take this full figure, right, now here if you take this full figure, this is going to be V and this is going to be L. So here you'll be having a theta. Now I'll show you. Now if you check this here, that right, V is this, right, and this is L and this is D. Now how to get this theta? Sin theta is equal to V by D. Now from this figure you are going to get this, right? No, it's not going to be V by D. It's going to be V by L, right? Sin theta is going to be V by L, right? Here, if you take this, now this is L, and here you will be having V. Then sin theta is equal to V by L, right? This is going to be correct. Sin theta is equal to V by L. Now here you can see that I have written that sin theta is equal to V by L, where V is equal to sin theta, where L is equal to K S dash C into sin theta. Now you can write that S dash value again, that is V is equal to, right, here see that V is equal to Ks cos theta plus C into sin theta, where S value, S dash value will be here. See that S dash value we have shown, no, S dash is equal to S into cos theta, right? Now after this, what is going to be there? See, you have to put all the values together and you can get the formula here. Here, see here I can show that here. Now here you can see that, right, V is equal to Ks cos theta into sin theta plus C sin theta. So this is going to be the formula for V, right? And you can write that formula like this also. So here I have written, see that V is equal to right, by multiplying by 2. If you multiply by 2, what you are going to get here is Ks, V is equal to Ks into sin 2 theta by 2 plus C sin theta. That is going to be a vertical component. This you have to remember to get the V value, because see that sin theta cos into sin theta plus 2 sin theta is there, right? Here C sin theta is there. Now that is going to be the equation. Sin 2 theta is going to be there if you add here, so that multiplication will be there. So that I have simplified by dividing 2. So it is easy that V is equal to Ks into sin 2 theta by 2 plus C sin theta. Now that is going to be how you are going to get V value. Well, my friends, these are the equations that what we are going to use, and we are going to solve few of the problems there. So these two derivations are very important, because of these only, by using these only we are going to solve few of the problems. Just keep thing in your mind. I'll remind it, right? I'll just try to tell you that what we have did here. See, we have started with the principle of stadia tacheometry, where we have seen how to get the K value and how to get the C value, right? So here I have shown K value. K is going to be depend on the this 34.22, and then we came to the theory of stadia. There we have derived the D equation. D is equal to F1 plus D, and then we simplified it to get the D is equal to Ks plus C, where K is the multiplying constant and C is the additive constant. Then we came to the two different cases where you will be having the or you'll be having the line of sight horizontal when staff held vertical, then D is equal to Ks plus C, and you can easily determine the RL of different points by using that. Now the next and the last case, that is case 2, here we have got the distance and elevation formula, where we have got D is equal to Ks cos square theta plus C cos theta, and V is equal to Ks into sin 2 theta by 2 plus C sin theta. Now this is what all from my side. Thank you.